Hello, in this video we study comparisons of series. Let's consider the following theorem before we move to examples. Suppose that you have two series AN and BN such that AN and BN are non-negative and AN less than or equal to BN for all n. Then if the smaller one, the series of AN diverge, then the bigger one also diverges. And if the big one converges, then the smaller one converges. So that is direct comparison. I have to mention one thing, right? Again, we are interested in convergence of those series. So the condition for all n may be replaced by another one, such that like you may start from a big number m, not necessary for any or for any n. Does that make sense? So like previous video, right, if we are interested in convergence, we may cut a finite number of terms in each series. So this comparison still works. Does that make sense? Like not for every n, so you might have this inequality for n bigger than 1 million. This is also okay. Does that make sense? All right, let's consider the following example. You have series 1 over 2 plus 3 to the n from 1 to infinity. Okay, so when you see this series, so you may think about the one, look like this, 1 over 3 to the n from 1 to infinity. And you predict that, yeah, maybe this series and this series converge or diverge at the same time, right? So, but we know that this series converge because that is geometric series. Because you can rewrite this as n from 1 to infinity n 1 over 3 to the n. And this series converge because 1 over 3 in this case less than 1. So I hope you remember that. Geometric series. So you may think, yeah, this guy may converge, but you need to compare this series with this one. Okay, so if you look at this theorem, so you might think, yeah, AN, this is your AN, and maybe this is your BN, right? So now let's compare. AN is equal to 1 over 2 plus 3n. Okay, and Bn around here equal to 1 over 3 to the n. Of course, you can see this An less than or equal to Bn and all this greater than or equal to 0. This happens for any n. So that means the first series converges. Okay, so that is observation. Let's write the solution in here. Okay, so we have An equal to 1, 2 plus 3n less than or equal to 1 over 3n equal to Bn. And the series 1 over 3n and from 1 to infinity equal to series and from 1 to infinity over 3 to the n. This converges. That is geometric series. Don't forget, for geometric series, the index runs from 0. But it's fine. You can add and subtract a finite number. That's not a big deal. That is still converges. Then, series AN converges. Does that make sense? So, it is pretty nice, right? But the difficulty, when we apply this comparison is sometimes you cannot find the corresponding series because here you need to find a new series. Does that make sense based on the original one? So I think we discussed a lot about similarity, right? similarity. I say, in this case, 1 over 2 plus 3 to the n is similar to 1 over 3 to the n. Okay, at infinity. So from here, I will write here 1 over 2 plus 3 to the n, and from 1 to infinity, and 1 to the n, 3n in here, and from 1 to infinity, converge or diverge together. And you see, since and from 1 to infinity, 1 over 3 to the n equal to 1, 3 to the n, and from 1 infinity, converse. We have that the original series converse. So, this is also a solution. And in this solution, you don't have to predict. You don't have to predict this series. Of course, this series also comes from this one. But in my opinion, I would say this easier, right? This is easier than the previous one. So you just, again, right, similarity and infinity, you ignore all terms. You just pick the term with the highest degree. And in this case, 3n to the n is exponential function, and 2 is just a constant. You might ignore 2. That will not affect your series at infinity. Does that make sense? I mean, in the sense that, that does not affect the conversions. Okay? Let's consider another example. And I again will show you two solutions. So the first one, okay, series 1 over 2 plus square root of n, right? And from 0 or from 1, whatever, to infinity. So when you see this one, you might think, yeah, let's compare with 1 over square root of n and from 1 to infinity. Okay, so we write the solution. We have 1 over 2 plus square root of n less than or equal to 1 over square root of n. And of course, this is greater than or equal to 0. Okay, then from here, series 1 over 2 plus square root of n, and from 1 to infinity, greater than 0 and less than or equal to series of, oh no, it does not look good to me. Anyway, so maybe this is a mistake we need to avoid in the future. And from 1 to infinity. Okay, so look at this. This series diverges. Okay, so you cannot do conclusion that this series also diverges, because if a series is less than a divergent series, that does not mean that that series also diverges. So this is a wrong direction. Does that make sense? So you see, we need to compare with another one, but you think like this. So this series diverges, right? So you might think, yeah, in this case, maybe the original series also diverges, but you don't want to use this comparison. You want to use another one. All right, so how? That somehow we need to make like 1 over 2 plus square root of n should be greater than something in here with 1 over square root of n. Does that make sense? And okay, it turns out that yes, it's not that difficult. So you may use like 2. How about that? Or 3. Or 2, let's say 2, right? Why? Because 2 square root of n greater than square root of n plus 2 for n greater than or equal to 4. You see, you don't need for any n. Just start from big enough number. So in here, you get square root of n greater than 2 for n greater than or equal to 4. Okay, so that means this inequality is true. So from here, I get sum of 1 over 2 plus quarter of n, and from 1 to infinity, greater than or equal to sum 1 over 2 quarter of n, and from 1 to infinity. And that is 1/2. That is P series, right? And from 1 to infinity. This is equal to infinity. Because the P in this case is equal to 1 over 2, less than 1. So that means this series is infinity diverse. Does that make sense? So you see, sometimes we might do these mistakes. Okay, at least, at first I did that, but we predict that, yeah, these two series should be related, right? So if we use comparison, you can see the following. Sorry, not comparison, similarity. I write series of 1 over 2 plus quarter of n, and from 1 to infinity is similar to the series 1 over quarter of n, and from 1 to infinity. I just ignore 2. Does that make sense? So this is equal to infinity. From here, the series 1 over 2 plus quarter of n is also infinity. Done. That was. So you see, sometimes if you understand the idea of similarity, you can work out very well. Okay? Now, let's consider another test, limit comparison test. And you can see that actually that is some kind of similarity, okay? Say limit comparison test. So suppose that an and bn greater than 0, and limit of an over bn equal to L. So you consider limit of quotient of two, general terms of two series. And let's say this guy is positive and finite, okay? Then two series an and bn either both converse or diverse. Okay, so what does it mean? Look at this. How to understand that the limit of the quotient an bn equal to some L bigger than 0. That means these two series are similar. Right? Are similar. Because the limit of the quotient an bn is just a number that bigger than 0. So let's say it seems like, yeah, you can see an, it's just scalar multiple of bn, right? In this case, an is similar to lbn, but since you multiply by a scalar, that does not affect on the convergence of your series. So that's why two series converge or diverge together. Does that make sense? You can see a very short proof in the textbook, but that is just a very, very short explanation. All right. So let's consider the following example. So what we're seeing here, 3n squared minus 4n plus 5, and from 1 to infinity. Okay, so let me show you the similarity, okay? So we want to see if this series converge diverge. By similarity, we pick the term with the highest degree, so f1 over 3n squared. These two series are similar, and that is nothing but 1/3 1 over n squared, and from 1 to infinity. And this is finite, this conversion. because the p in this case equal to 2 with bigger than 1. P series, don't forget that. Then from here you see that this series also converge. Okay, this is about similarity. Let me write here. Okay, so if you want to use comparison, you would think that you compare this guy with this guy. How about that? Or you might compare with just 1 over n squared. Okay, so let's compare an equal to 1 over 3n squared minus 4n plus 5 and bn equal to 1 over n squared. So I have the limit of an divided by bn, and in approaches infinity equal to the limit of, so you multiply, okay, let's say this is an, you divide by bn, that means you multiply by the inverse, right? So you multiply by n squared. Let's write that and then compile them together. Limit of n squared over 3n squared minus 4n plus 5, n approaches infinity, and this limit is just 1/3. Okay, let's try one more step in here. Limit of n squared over 3n squared, n approaches infinity, and equal to 1/3. And again here we use similarity, right? Because at infinity this term will lead the behavior of the whole polynomial. So the limit of this guy equal to a finite number, which is positive, right? In this case, 1/3. That means an and bn converge or diverge together. And again, you need to consider that, actually, and since bn converse, we have that an also converse. Sometimes I write converse, so that is the condition that less than infinity, okay? Because all these series are positive. So you might think about choosing similarity, okay, if you want, or if you want you can choose comparison, limit comparison. Okay, so let me show you more examples about this, because that is the best way to understand them. So you have square root of n over n squared plus 1, and from 1 to infinity. Let me use the similarity. Okay, this is similar to what? And from 1 to infinity, square root of n over n squared. So I ignore 1, right? And this is nothing but 1 over n 3 over 2, and from 1 to infinity. You simplify. You write square root of n is n to 1/2, right? And then here you subtract 2 by 1/2, you get 3 over 2. So this is conversion, because the p in this case is 3 over 2, bigger than 1. So this guy converges. Does that make sense? So it looks very, very pretty, right? Very simple. All right, let's move to the next example. So let's make that more complicated, right? N squared minus 10 over 4n cubed minus n. And from 1 to infinity. So according to similarity, you get n squared over 4n cubed, and from 1 to infinity, and that is 1/4. You have 1 over n, harmonic series, and this is infinity. From here you see this is diversion. Okay, let's consider the following one. N 2 to the n, and here you have 4n cubed n from 1 to infinity, 4n cubed plus 1. All right, so this is similar to series from 1 to infinity and n 2 to the n over 4n cubed. You ignore 1, right? So you have n from 1 to infinity, 2 to the n, 4n squared. So you know that exponential function is much faster than polynomial. So here you write 2n is much faster than n squared. Then the limit of 2n over 4n squared and approaching infinity is not 0. That means the series 2 to the n 4n squared diverse. Does that make sense? And then from here we get the original series also diverse. So of course here we use similarity, but you may rewrite all these solutions in terms of limit comparisons. Does that make sense? So I think I finished my video in here. We still have a lot of examples in homework. Please practice a little bit to get more, experience and better feeling about how to use comparison, similarity, okay? And sometimes, you can do limit comparison. But again, right, if you can use similarity, that will save a lot of time. And of course, you might avoid limits. For example, in this case, so this is your AN, this is your BN. Firstly, you need to find BN, right? And then you need to find the limit. And it is pretty long. So similarity is some kind of comparison, is some kind of limit comparison. Does that make sense? But that helps you to, again, avoid limits and save a lot of time. So I hope that you enjoyed the video. If you have any questions, please feel free to let me know. Bye.